Hello, everyone. Welcome to this breakout session. Thank you so much for being here. My name is Satish Iyer. I'm a senior product manager here at Google Cloud, and I'm joined by my brilliant colleague, Tanvi Srivastava. I know you have a lot of sessions that you attended this week, so we are going to make this one count. Today, we are here to talk about a very exciting, stressful topic, maximizing the value of your compute. So here's the game plan for the next 45 minutes. We are going to start with the compute landscape, and we're going to discuss the challenges that we're all facing today. I'm then going to introduce you to the flexible consumption portfolio at Google, and then Tanvi is going to walk you through a blueprint for how you can actually build and automate this flexibility using the tools that we have today. So let's dive right in. So let's start with the classic cloud optimization journey. We all know this one very well. When you bring a brand new workload to cloud, you start with your on-demand. On-demand is great. It's flexible. It meets your needs. You learn about your usage patterns. As your workload matures and you get to a production state, that's when your FinOps team taps on your shoulders and says, let's lock this down. And that's where you get into the 1 year and 3 year commitments with cut discounts. But if your workload is still growing and you want the flexibility to switch between different machine families, let's say between N2 to N4, that's when you use things like flexible committed use discounts or flex cards. This journey works beautifully for standard web services and databases. AI, as we all know, is not like a standard web service. So that brings us to the core of today's topic in terms of when we apply the standard procurement model to AI, things break. They break in 3 specific ways. Number 1, training. You need 100 interconnected GPUs for a 28-day training run. Now, you can't go and sign a 1-year commit for a 4-week job. So you also cannot rely on standard on-demand and just hope that 100 GPUs would magically appear on a Tuesday morning. So how do you overcome a challenge like this? The second challenge is around inference. This one keeps a lot of infrastructure teams awake. The inference traffic is wave-shaped. So you really have a tough choice. Like, do you rely on best effort on demand, or do you reserve a 24/7 capacity for your absolute peaks? I call this the hoarding tax. The third problem is around cost optimization. Now, we all love Spot. You want to run massive batch analytics. Spot is great. It gets you 90% discounts. Brilliant. You just deploy it. But if you deploy it blindly without knowing the physical constraints of a region, you end up getting preempted over and over again, and your job never finishes. So AI is unique in many different ways, but these are 3 specific problems that we are going to touch upon today in our session. This brings us to the core of the session topic, what Tanvi and I are going to talk to you about today. We had to change the way we think about AI infrastructure. The old paradigm of reserving chips, allocating chips is over. We have to stop treating capacity as a binary choice where you either reserve 24/7 for your peaks or you just roll a dice. The future is shifting towards orchestrating access to capacity. That's where flexible consumption comes in. Flexible consumption is about matching your compute spend to the actual workload pattern, or at least get as close to it as possible. The goal is not just to save a few dollars on the cloud bill, but it's about building resilience against stockouts. It's about making your compute infrastructure bend instead of break when the traffic hits. To do that, you need a system designed ground up for AI. And this is where Google's AI hypercomputer comes into picture. Google's AI hypercomputer has purpose-built hardware in the form of GPUs, TPUs, CPUs, all with optimized software frameworks like JAX and PyTorch, orchestrated natively by GKE. This deep integration across the stack from hardware to software and platforms really makes it easy for us to deliver flexible consumption seamlessly across all workloads. So what are the actual tools for flexibility? I like to break this down in analogies, so play along with me here. Let's look at your steady state baseline usage for capacity. You have your 1 year and 3 year CUDs. 1 year and 3 year CUDs are like signing a lease on an apartment. You own the space 24/7, it's yours, it's highly discounted, you're paying for it whether you're sleeping there or not. The second is future reservations. Future reservations are like booking a hotel block for a conference in the future. You lock guaranteed capacity in the future and it cannot be canceled. But what about your spiky and batch workloads? This is where the flexibility journey really starts. DWS FlexStart is like waiting in a line. If your workload can tolerate a little bit of wait time, say it's an asynchronous batch job, you just tell us your flexibility window, we queue it, we find the space, and you get up to 50% discount when it's ready. DWS calendar mode is a short-term guarantee. It's a short-term reservation. So let's say you need a massive cluster or interconnected GPUs for 14 days. No problem. You use calendar mode, you book it, you use it, and you give it back. And Spot VMs. This is again, like you're all very familiar with Spot, so we are going to see some new exciting things on Spot today. But it's incredibly cheap. It's up to 91% off. But you accept the risk of preemption, so it's perfect for any fault-tolerant workloads or analytics. So how does this really map into the reality of the AI world? If you're doing online inference, you need some level of certainty. So you use reservations as your main source of capacity, with some flexibility built around it with on-demand and Spot VMs. As you move down the stack or move up the stack, to model fine-tuning and batch inference and online and offline experimentation, this is where DWS FlexStart and Spot really come in very handy. These consumptions give you access to the same accelerators, but at a fraction of the cost. So you can optimize your cost as well as segment your workloads properly. If you take one thing away from my section today, it is this. Stop treating every chip, every accelerator in your cluster like it's mission critical. It's not. Over-provisioning 24/7 reservations for background batch jobs is an easy way to burn through your budgets for compute. You have to segment your workloads by your tolerance for wait, your tolerance for interruption. And if it's mission critical, you have to secure your baseline. If it's scheduled, you can use calendar mode. If it's time flexible, use FlexStart. If it's fault tolerant, use Spot. Defining this segmentation strategy is the first step towards building flexibility. Once you've segmented your workloads, how do you actually architect them for flexibility? The most important rule here, especially in the agentic AI era, is to move away from single point of failure hardware requests. True flexibility means designing multi-dimensional fallbacks. These fallbacks can be in the form of shape flexibility, generational flexibility, location flexibility, and more. Shape flexibility, like if you can't get a 8 GPU VM, configure your workload to accept 2 4 GPU VMs, if it's possible. Generational flexibility. If you can't get the latest C4 or A3 machine, fall back into C3 or the previous generation A2 machines. Location flexibility. If US Central 1 is running hot, try and fall back to US East 4 to get the same capacity. The goal here is to define the intent and let the system find out the right capacity in the right zone at the right price for you and make it work. Now, defining this fallback strategy is great, but nobody wants to keep hunting for capacity on a day-to-day basis. So this is where the need for automation comes in. GKE Custom Compute class is a great way to do this. It allows you to declare your compute flexibility directly in your infrastructure as a simple code. Looking at this YAML on your screen here, you can see that you can set up an automated hierarchy where you can tell GKE to first try to place this workload in my reserved discounted capacity. If that pool is full, start hunting for spot capacity. If spot gets preempted, fall back to DWS FlexStart in their queue. By writing these declarative rules, you eliminate the manual toil, and your infrastructure automatically routes around stockouts and optimizes for cost without your intervention. This, again, to show you how this all comes together in a real world, we have put together a mock case study here where we'll walk you through this. To do that, I'm going to hand this over to Tanvi and take it from here.
Thanks, Satish. Hi, everyone. My name is Tanvi Srivastava, and I'm the product manager for Spot VMs at Google Cloud. So for the next few minutes, here's the plan. We're going to use my favorite method of learning, the case study method, and we're going to step through a mock case study about a company that's about to launch a new product. Now, they need resources for this product, but they also must balance performance, reliability, and cost efficiency. Let's see how they apply the principles of flexibility that Satish just walked us through to achieve their goals. So we're going to step into the hypothetical for just a few minutes, but I promise we'll come away with some real-world learnings. Meet Nexus Retail. They're an e-commerce marketplace, and they are preparing to launch a new product. The product is called the Nexus AI Shopper. It's a massive generative AI personalization engine, and they want to launch it right before the busy holiday period. Now, there are two distinct problems they have to solve. One, they need 64 GPUs to train their foundation model on a new seasonal catalog. And the second challenge, they need to scale to 100 GPUs daily to serve incoming traffic from busy shoppers during the holiday period. Now, one way to address this challenge is to buy or hoard 100 GPUs on a 3-year committed use discount, also known as a 3-year cut. But that is going to be suboptimal here, because the peak capacity of 100 GPUs is not needed constantly. This is going to create underutilization and therefore waste. They have a strict mandate. They must execute this launch without paying the hoarding tax. So it is absolutely critical for Nexus Retail to truly embrace the principles of flexibility as they architect their solution. So what should Nexus Retail do? Let's unpack the first problem. Phase 1, orchestrating their training run. Here, they want to train and finalize their model that powers the Nexus AI Shopper. So the team determines they need 64 interconnected GPUs for exactly 14 days. This is ideal for DWS calendar mode. Using DWS calendar mode, Nexus Retail can book 64 GPUs weeks in advance, ensuring data pipeline and compute alignment. Now, this is guaranteed future capacity. They pay only for the 14 days for which they use the GPUs, zero waste, and their mandate is satisfied. So what is DWS calendar mode? If this is something you haven't experienced before, DWS calendar mode provides up to 90 days of reserved GPU and TPU capacity for your AI ML workloads without the need for long-term commitments. Capacity is co-located, which makes this model a great fit for model training, fine-tuning, and experimentation. Similar to a flight or hotel booking experience, calendar mode makes it super easy to search for and reserve ML capacity. So you simply define the resources you're looking for, the quantity you're interested in, your start date and expected duration, and within a few seconds, you'll see the available capacity and be able to reserve it. Calendar mode is generally available, so it should be accessible to everyone over in this room here. All right, let's go back to the case study. So let's look at the second challenge, architecting for serving. So the model is now trained. Now Nexus Retail wants to serve it at scale. They estimate needing a maximum of 100 GPUs daily for their peak usage. But their average usage is actually much lower. Again, if they simply reserved the 100 GPUs, they would be paying for underutilized capacity. So Nexus Retail decides to segment their workloads by their characteristics and map them to the corresponding flexible consumption model. They come up with 3 buckets. Bucket number 1, 60 GPUs are required for real-time user-facing inference, so suggesting products the moment a user clicks. This is their mission-critical baseline. Any downtime here directly impacts revenue. So Nexus Retail should go ahead and reserve these 16 GPUs with a 1-year cut for maximum capacity assurance. Bucket number 2, another 20 GPUs are needed for asynchronous inference, like updating new catalog items in the background. This is an important task, but it's non-immediate. It can tolerate waiting in a queue. There's start time flexibility. So this is ideal for DWS Flex Start. And then bucket number 3, the remaining 20 GPUs are dedicated to batch inference for evaluating new pricing models and analytics. These are fault-tolerant and cost-sensitive workloads that can tolerate being interrupted or restarted. Spot VMs are a great fit here. So you see how, by using a 3-pronged approach and mapping their workloads by their characteristics to the flexible consumption models, not only is Nexus Retail able to maximize the value they get out of their compute, they're also able to minimize waste and eliminate the hoarding tax. So we talked about FlexStart VMs a little bit on the previous slides. If this is something new to you, what is FlexStart VMs? FlexStart VMs provide uninterrupted runtime of up to 7 days if your workloads are flexible on start time. So this is ideal for defined duration tasks, such as model fine-tuning, batch inference, HPC, research experiments, that don't necessarily need to start immediately. They can tolerate waiting a little. And in exchange for this start time flexibility, you get 2 major benefits. You get improved obtainability and cost-effective pricing. So FlexStart VMs are up to 50%, offer 50% savings of regular on-demand instances. They're available across GCP, be that through GCE, GKE, Vertex, Google Batch, Dataflow, Dataproc, and more. And they support all GPU types and TPUs. Let's talk about spot VMs. So if you have workloads that are batch or fault tolerant, spot VMs are a great way to lower your cloud bill. Up to 91% off of on-demand, spot VMs provide the same performance and machine types as regular VMs. Now, they are preemptible at any time, so you want to make sure that the workloads you place on spot VMs are either easily checkpointable, stateless, or restartable. Today, we are excited to share 2 new developments related to spot VMs with you. Now, if you're familiar with Spot on Google Cloud today, you know that the default preemption notice that we offer is 30 seconds. You'll be happy to hear that we now also offer a full 120 seconds of guaranteed preemption notice, very easily configurable by a self-serve API flag at the time you create the Spot VM. And really, this is to allow more time to perform cleanup operations before the VM gets taken away. Second improvement. We heard your feedback loud and clear over the years that the lack of capacity visibility and guidance around spot VMs can often make them feel a little bit like a black box. So today we'll talk about the capacity advisor for Spot, which helps here. Let's do a little deep dive. So if you've ever found yourself in one of these situations or all of these situations, you're in the right place. You use spot VMs, and perhaps you've wondered, I want to make real-time decisions on which spot VMs to pick and where to deploy them. I want guidance on the likelihood of preemption so I can make smart choices about where to deploy my workloads. Or I want to expand to new regions. Before I enter a new region, I want to get a sense of what are typical prices or preemption rates in those regions. Well, you're in the right place. Let me share some details. So Capacity Advisor for Spot, first of all, offers an intuitive yet powerful API that provides real-time guidance on capacity obtainability and likelihood of preemption. Let's look at the components of this API. So on the left are the inputs. you describe what you're looking for. So you describe your instance flexibility policy. Again, think back to how Satish explained the concentric circles of flexibility. This is where we codify them. So you specify your instance flexibility policy, define which machine types are acceptable. Perhaps you're flexible across N2, N4, C3, C4. This is where you specify that flexibility. You also specify your distribution policy. Maybe you're looking for all capacity in the same zone, or maybe you're OK with the capacity being split across multiple zones. The model is spot, and you specify the quantity of VMs you're looking for. Do you need 10 at this time, 100, 500, 1,000? You specify what you're looking for. And on the right are the outputs of this API. The API provides two new scores. The first one is an obtainability score between 0 and 1. Higher is better. It indicates a likelihood of successfully obtaining the requested number of spot VMs. So if you get a score of 0.9, that means high likelihood of success of being able to get those spot VMs right now. Conversely, 0.1 means low likelihood, which is a signal to you to look at other VM families, perhaps other zones, other regions. Okay? The second signal provided by this API is an estimated uptime, which is the estimated minimum duration for which you can expect the spot VMs to run before they experience preemption. So this gives you a sense of preemption risk associated with your deployment. Let's look at an example. So these are the inputs I'm going to provide to this API. You look at the green box. That's my instance flexibility policy. Turns out I'm flexible across N2 standard 8 and N2D standard 8. My distribution policy shows me that I will accept this capacity in 2 zones. I'm OK with US East 1B or US East 1C. And I'm looking for 100 such VMs. Let's look at the output. So with a high obtainability score of 0.9 and an estimated uptime of 3,600 seconds, an hour, the API recommends that we deploy all 100 VMs as N2 standard 8s in US East 1C. This is the best recommendation that the API found at this point in time. Because the obtainability score is high, you have a high likelihood of obtaining this capacity if you act now. Now, there might be cases where the quantity of VMs that you're looking for might not all be available in the same zone, or might not all be available at the same machine type, right? So in this example, the API tells us that, hey, you can still get the 100 VMs you're looking for, but you're going to have to distribute them as 80 N2 standard 8s in East 1B and 20 N2D standard 8s in US East 1C. But the sum of those parts together still get you the scale that you were looking for. So the point here is because you expressed flexibility to the API was able to use that information to get you the best outcome. The more flexible you are, the more we can hunt for you in the background. This API will hunt for you and provide you the best possible response. In addition to the API, the capacity advisor for Spot will also provide 2 helpful UI views. Now, these are early previews of what's to come. So on the left, you see a map. This map provides a view of obtainability across regions and zones. So you search for what you're looking for, the machine type, the quantity, and this view shows you on a global scale where we could find matching capacity. So perhaps today you're only using US Central 1 and US East 1, and it turns out the regions are constrained, but maybe US West 1 has what you're looking for. This map shows you the possibilities beyond your search criteria. And on the right is a tabular view, which allows comparability between VMs. Now, we know that when you use Spot VMs, oftentimes you want to compare what do typical preemption rates look like for machine 1 versus machine 2, zone 1 versus zone 2. This table is going to allow that comparison, sorting. It will also show you prices, current prices as well as price history, preemption rates today versus in the past. So the idea here is to give you a sense of what is a typical Spot experience in a particular zone, region, machine family, so you can make smart choices as you look to expand. Now, today we shared an example of the capacity advisor for Spot on general purpose VMs, but this API is also available for Spot GPUs, and it is also coming to other consumption models soon. That actually brings us to the key takeaways for the session. So there's 4. Number 1, stop paying the hoarding tax. So segment your workloads, secure your mission-critical baselines with cuts and reservations, and use flexible consumption models for the rest. Shift from provisioning to orchestration to reduce single points of failure. Build automated multi-dimensional fallback chains which leverage flexibility along the dimensions of shape, location, and generation. Visibility is your superpower, so leverage intelligence provided by the capacity advisor to make smart choices on where to deploy your workloads. And finally, match the mechanism to the outcome. So reserve your clusters for massive launches, but trade immediate latency for cost savings for your batch training using FlexStart and Spot. That is it for what we have for today. There are a couple other sessions happening later today that are relevant to the topics and themes we've talked about. And I think we have time for questions. Please leave your feedback. Helps us improve the session for next time. But we'll stick around for Q&A now. Otherwise, thank you for being here today. We really appreciate your time.